can you see my presentation?
We do.
Perfect. Yes, my name is Johannes from Sweden. Actually, I'm sitting in Turkey now, but no one would know that anyways. My talk will be about information extraction with text pattern recognition. Yeah, let's begin. I will talk first a bit about the concept of information extraction and what it is for people that doesn't know it, and continue with the previous work that my work is mainly conducted upon, followed by our approach and the results of that and some conclusions. First, I will now start broad and talk about how much information that is flowing across the globe at the moment. Only for 2021, we have had like 250 million megawatt hours of power consumptions, 63 million computers sold, and 120 exabytes of data is being transmitted. And just imagine what we can do with all this information if we can just process it and handle it in a structured way. And you might think that this is everything there is, but it also is about the information gets lost when you are receiving the information and interpreting it in a certain way. There are implied informations that we need to consider as well, where there is information not explicitly expressed in text. And then there is also irrelevant or fake news, which is information that we might not be interested in. And all these types of information I'm touching upon in this research. So first off, what is information extraction? We can consider this text from Wikipedia, and information extraction basically consists of 3 steps. First, we identify all the entities in the text, followed by all the relations that we can connect these 2 types with. And then it's all about connecting which entity should be connected to which relation in a so-called triple, as you can see to the right. And if you can do this for the whole text, we get a sense of what the text is about in a more structured way, where we can do data analysis or anything on this type of information. So our post algorithm consists of 3 steps. First, we need to convert the text into some sort of understandable information by the computer with a bag of word algorithm that basically encodes it into vectors. And then our information extraction algorithm that consists of several other models, trained or pre-trained. And eventually we will receive some sort of triples out of this. And you might wonder, what can we do with this kind of application? Because triples in itself might not be so useful for the human person, but if we can use these triples in sort of analysis to identify what are we writing about or reading, maybe we can do summarization of the text based on what's actually said in the text, not the bias or the judgments and such, by just the information. We can also construct what you see on the screen here, a sort of a knowledge graph with all the entities and relationships with that we find in a huge data set. And this work doesn't include this, of course, but just to get an idea of what we want to achieve with it in the end. So this approach is considering both 2 multi-language. So we consider both the English language and the Swedish language, which is because we are from Sweden and we want to use it, of course, in the society. So first off, as I said, we train the text in a bag of word algorithm that is context aware of where the words are occurring. So you can say, for example, I'm not sure if you've heard about Michael et al. He you can do this kind of computation where you say king plus woman minus man equals queen. So with these kind of vectors, we can sort of understand where the word is coming from. And from this vectors, we also compute the part of speech of the words. Is it a noun, subject, verb, and so on? And analyzing the dependency parsing of which words are depending on other words. What are they referring to? We also include a co-reference algorithm that identifies words like he, she, it, and tries to find which words they are related to. And also a named definition that identifies the entities that we want to combine all together into these triples that we will find in the end. Now, most of these algorithms are pre-trained already, so we actually don't train them ourselves, but the new work that we have been conducted is mainly the how we combine them together. Some previous work, open information extraction, and yeah, some others if you're interested. So the two main algorithms that we have compared our approach with is one, open information extraction, which based on a neural network approach where you train to find these triples in a text, and they have been evaluating and training on a foster data set. And the other one is minimize information extraction, which is a clause-based approach where you identify pairs of words in the text that could potentially be a relation between an entity and another entity, and suggests propositions from them that they either discard or approve. And our approach is somewhere in between these two algorithms, and that's why it's very intuitive for us to just evaluate these three algorithms together. So there is this question, can our proposed information extraction algorithm compete with the state-of-the-art algorithms by using common grammatical rules for Germanic languages, such as Swedish and English? Does the proposed information extraction algorithm perform in terms of accuracy on multiple Germanic languages? So we evaluate that kind of metric as well. And to what extent can the information extraction algorithm be enhanced when we combine these three algorithms together? And maybe we find even more accurate predictions. So the main algorithm is, as I mentioned, name recognition, part of speech, and dependence parsing is the core three main models that we use to identify the entities and the relations. And the named recognition identifies time, people, organizations, locations, and events as entities. And if we can find a part of speech word that is a verb, then we consider it as a relation, but only if we can connect it to another entity in the next step. We also add, from these entities that we identify, we add additional filters such that entities can only be nouns, and relationships has to have a sort of a relation between the entity, and it cannot be a subject or a noun, basically. And with these rules, we can reduce the number of triples and find more accurate ones. And this picture, if you've worked with Stanford University models before, you've probably seen this kind of dependency tree. If we have a sentence, I have a yellow ball, we can see that have is the root word in the sentence that refers to both I and ball. And in such way, we know that have has a relation between I and ball. And that's how we connect the relationships with the entities. And yeah, for each relation we find in a sentence, can we find entities underneath? Then we make triples out of them, basically. And for each found triple, we also need to verify that it actually has one entity, one relation, and one entity, and that they are related to each other. And the results, we have used Wikipedia dataset for both Swedish and English, and conducted a quantitative part where we evaluate more of how it would perform in when we have a lot of data. We tried 100,000 sentences and evaluated it across the algorithms and investigated how many newly found triples per sentence we can find in an iterative process. And also the research investigation has also been conducted, where we have manually evaluated 1,000 sentences, several people, and conducted more like an accuracy sort of evaluation on these fewer sentences. So the quantitative results looks like this. The OpenIE is the huge red blob, which detects the absolute most triples, and GenerateIE, the name of our approach, detects a bit more than MinIE, but still not as much as OpenIE. If we look at the overlap between the algorithms, I know it's not the sizes of these overlaps are not in scale, but at least there is not that much overlap between them as there are entities or triples found in each circle. And thus, even if we're just using one, we are also missing a lot of triples according to this. Yeah. And the extracted relationship and sentence, you can see here, the x-axis is the number of sentences we have been analyzing so far. So at 2,000 sentences, it's around 5,000 triples that OpenIE finds, and maybe 2,500 for the other two. Yeah. And if we look at the investigation instead, here we have a bit fewer triples that we have evaluated, and we can see it's the same kind of distribution, that OpenIE has more found triples than GenerateIE and MinIE, and there is even less overlap between them. We've also been looking at these kind of graphs where we can see that, yeah, some of the triples between GenerateIE and OpenIE are in common in the middle, the green circle basically, and then there is some triples that only OpenIE finds, and some triples that GenerateIE finds. If we're looking at the manually labeled evaluation, we can see that if we combine all the triples for all the algorithms, it's around 900, or 1,000 triples in total, whereas a bit less than 400, maybe 300 triples have been correctly extracted if you combine them all. For OpenIE, there's almost half of the triples that we did not find of all the triples extracted, and the correct is also halved to 200. So we can also look at if we combine the triples that both OpenIE and GenerateIE finds, it's a lot less, but then the accuracy might also be higher, since it's almost the same number of correct as extracted ones. And if you match all, then it's barely any matches at all. Yeah, and this one was for the Swedish language. And if we look at the accuracy actually goes up the less triples there is, of course, but for the match all, which has an accuracy of 1, it's also like only a couple of triples. So if we want to use the algorithm, it also depends quite a lot about what's the purpose of it. If you want to extract as many triples as possible, then you would probably consider using all 3 of them in the left side, while if you want to have an accurate model, but not too restrictive, then matching both open information extraction and GenerateIE yields a higher accuracy than, for example, GenerateIE and MinIE or so, but with no real significance. And the conclusion, yeah, OpenIE can perform as good as our model in terms of accuracy, although it also yields a lot more triples. The combined algorithms perform even better. Yeah, OpenIE found almost 4 times the number of triples, plenty of correct triples that OpenIE are missing. If we want to take this research further, I would say we would like to consider these extracted triples that are correct and use them to implement a knowledge graph that we can derive additional triples that are not in the data set, but because of the entities, we can deduct what their hidden triples are going to be. And also explore different languages and see if we can apply it there, since it's such a easy to adapt depending on the language, as long as it's a Germanic language at least. Maybe there is a bit harder to find the working model for the Chinese or Japanese or any such languages with a bit different grammar and structure, sentence structure. Yeah, thank you for listening. It was a short presentation today. I hope you enjoyed it. Any questions?